Okay, so I'm going to lecture in section 3.5 this morning. One good thing about section 3.5 is there's absolutely no algebra in the section, which in some sense makes it friendly. It's not a particularly difficult section, but it's a long section. There's essentially four big concepts that we need to master, and this is one of the rare sections where I just can't really just jump into the homework problems. I need to do a lot of warm-up. And if you printed out the handout, you'll see that there are a bunch of problems marked lecture problems. And it says the first few pages are problems that I will solve when I lecture. The problems labeled lecture are not homework problems. But if you don't watch this part, then you won't understand the homework problems. So this is just to make it so I can go through the lecture at a reasonable clip. You absolutely want to have your graphing calculator handy to do this section, and I think I know we're going to do a lot of graphs, and the standard window, the -10 to 10, the zoom standard is going to be fine. So I'm just going to go through the problems and maybe do a little bit more than I might do if I didn't feel like I had a decent amount of time. But lecturing, I get an hour and a half here, and I will use that hour and a half. So the first thing the problem 1 says is graph the function f of x equals x squared. So I'm just going to hit my y equals button and graph x squared. I'm going to hit zoom in standard just to get that standard -10 to 10 window going. So that's just a nice generic parabola with its vertex at the origin. So this is the graph of f of x equals x squared. And then the instruction said, then graph each of the following functions using your calculator and describe how the graph compares to the graph of f of x squared. So I'm going to leave this parabola graphed, and I'm going to graph the function in part A, x minus 3 squares. I'm only looking at this thing to the right of the equal sign. To the left of the equal sign is the proper name of this particular function, but that's maybe overkill. I just want it to be mathematically precise, and we're just going to graph what's to the right of the equal sign for all these parts of question 1. When I graph this, it's going to be another parabola. In fact, every one of the parts A, B, and C, the graph of the function in part A, B, and C is going to have exactly the same shape as the original problem. As a matter of fact, it's going to have exactly the same dimensions. When I hit my graph button and it graphs the second graph, these two parabolas are exact copies of each other. I call this graph a rigid transformation, which means the graph doesn't get distorted at all, it just gets moved. Those two graphs, if you slid them on top of each other, they'd fit perfectly. That says rigid transformation, believe it or not. What the instructions want me to do is they wanted me to graph both. So the second one graphs something like this. It's exactly the same shape, meaning if I slid the second one, it would fit perfectly on the first one as a rigid transformation. I want to describe how the graphs relate to each other, and this number 3 that's in the parentheses, or the -3 that's in the parentheses, is a big deal. And if I look at the vertex of the original problem, the vertex of the original problem, the original x squared, is at 0, 0. And if I could count this out, it's going to be kind of hard to count out, but it's horrible precision here. Let me clear out this function and see if that makes it easier to see where the vertex is at, and maybe it does. I see 1 tick mark, 2 tick marks, and there's 3, and then there's a 4th tick mark. This vertex is at the point 3, 0. So the initial function that had no parentheses, just the f of x squared, is a parabola with the vertex at the origin. My new function, which is a rigid transformation, which is the exact same graph, just shifted but in having a vertex in a different location. If I want to describe how the graphs compare, this graph is the same shape, or there's the same graph as it's the same graph of the x squared function, except it's moved or shifted. And to get from 0 to 3, that's going to the right 3 units. I'll say 3 units or 3 spaces to the right. So that's everything that's asked for in part A. I graphed each function. I described how my original graph and new graph compared. Part B, I'm going to do the same thing. I'm going to graph the f of x equals x squared again, which is a parabola that has its vertex at 0, 0. And I'm going to change my y2 now to x minus 4 quantity squared. I don't even need to retype the function. And let me only graph that. Shut this off. When I hit graph, I'm only graphing the function x minus 4 quantity squared. And if I look at this function, I count on the x-axis, I see 1, 2, 3. This function is a parabola. Its vertex is at the point 4, 0. And if I turn this graph back on, those two parabolas are exact copies of each other, meaning it's a rigid transformation that the new graph would slide right onto the old graph. So the new graph has exactly the same shape, except instead of having a vertex at 4, 0, at 0, 0, it has a vertex at 4, 0. So I'm going to say this graph, that how do the graphs compare? They're exactly the same, except the x minus 4 squared graph, I'm just using slightly different words just so you don't have to use the same words as me, is shifted or moved 4 units to the right. Hopefully, you can make a guess at how the graph for part C is going to look and maybe answer that question without even graphing. So I'm going to graph the x minus 6 quantity squared in place of the x minus 4 quantity squared. And when I sketch that graph, there's the original x squared. There's my new x minus 6 quantity squared. Those graphs are exactly the same shapes. And if I count to see where the vertex is, I'd go 1, 2, 3, 4, 5. It's at 6. So the new graph, instead of having a vertex at 0, 0, like the f of x equals x squared has a vertex at 6, 0. And if I want to describe how these are, the graphs compare, the new graph, the graph of x minus 6 squared, they're the same, exactly the same shape, except the x minus 6 squared graph, or the f of x minus 6 graph, is shifted 4 units to the right. So in general, if we have an x squared function and we're comparing it to some function that has x minus some number squared, this second graph is going to be the exact same shape, except it's going to be shifted to the right, whatever that number is, units. Two wants me to do something similar. The instructions say start by graphing the function absolute value of x, and then graph each of these and describe how they compare. So I'm going to start off by clearing out the functions that I have in my calculator and graph the absolute value of x. To graph the absolute value of x, there's not absolute value bars. I have to hit the math key, go over to NUM. So I hit math, then the top I went to NUM. ABS is for absolute value. If I want to graph the absolute value of x, that's going to give me this function, the absolute value of x. And it's going to be a v. So an absolute value of x graph is similar to a parabola in some sense, but instead of having curved sides, it has straight lines. So I'd say that's a v with its point at the origin. Now I'm going to right under it, or right next to it, or on the same graph absolute value of x minus 2 and describe how those graphs relate. When I hit my graph button now, it's graphing the absolute value of x minus 2. So it's graphed both graphs, the original graph that had its point at the origin, and this new graph, it actually has its point at 2. The new graph that I drew, the absolute value of x minus 2, the point of the v is at 2. And if I want to describe how these graphs are related, they're exactly the same. They're exactly the same shape. This is a rigid transformation. The left and the right graph, you can put them right on top of each other and they'd fit perfectly. But the graph of the x minus 2 is shifted 2 units to the right. That's not supposed to be amazing. You'll notice that putting a minus inside a parentheses with a parabola function, the x squared, it shifted my graph to the right. Putting a minus inside under the absolute values also shifts the graph to the right. Hopefully, you could predict what the graph of part B is going to look like. So I want to compare the graph of the absolute value of x to the graph of the absolute value of x minus 4. I'll graph them both on the same graph. And when I hit my graph button, there's the absolute value of x. There's the absolute value of x minus 4. If I compare the two graphs, I count over to see where the point of the v is. It's at 1, 2, 3, 4. So when I graphed the two functions, the initial function, absolute value of x, it's a v with its point at the origin. This new graph, the absolute value of x minus 4, is an exact copy of those graphs. If I slid the new graph to the left 4 units, it would fit perfectly on the original graph. That's why we call it a rigid transformation. It doesn't distort the graph, it just moves it. And I'm going to say these shapes are the same, except that the absolute value of x minus 4 is shifted 4 units to the right. Hopefully you could predict the answer to part C, and hopefully you can maybe even sketch a crude graph of the absolute value of x minus 6 without even using your calculator. So hopefully you are starting to see some connections to these problems. This is what I'm going to predict, that my new graph is also going to be a v, but instead of having its point of the v at 0, 0, it's going to have the point of the v at 6, 0, and this graph is going to be the same shape as the absolute, so I'll say it's the same as the absolute value of x, except the absolute value of x minus 6 is shifted 6 to the right, which means when I graph this on my calculator and I change the x minus 4 to x minus 6, that second graph, its v should be at 6. If I count over and go 1, 2, 3, 4, 5, 6, is exactly what happens. So with both squares, if I put a minus inside a parentheses, it shifts the graph to the right. With absolute values, if I put a minus under an absolute value sign or inside an absolute value sign, it shifts the graph to the right. Next thing we're going to look at is putting minuses under the graph, under the square root functions. Problem 3, he says, start off by graphing the square root of x, and then compare how these graphs, describe how these graphs compare. So I'm going to do that just perfectly here. I'm going to clear out the functions that are in there, and then I'm going to graph the square root of x. I'm going to go second and x squared for the square root key, and this is just a graph of the square root of x. The square root of x is kind of a half a parabola on its side, and kind of starts at the origin. You'll notice all my seed graphs, this absolute value of x, the x squared, and the square root of x all kind of begin at the origin. This graph, it's a little harder to see that this is actually a rigid transformation, but it is. The graph is just going to be shifted, but this shape isn't going to be changed at all. So now I'm going to do y2 and graph f of x equals square root of x minus 2, putting the x minus 2 in a parentheses, and when I hit graph, I get something, it almost doesn't look like it's a perfect shift, but it gives me this. And this new graph, if you slid it over, it would fit perfectly on the old graph. And I would say that the new graph is the same as the old graph, but it's shifted to the right 2 units. Usually we get lazy and we just don't say this graph is the same as the other one. We just describe how it's different. And I'm just going to say it's shifted to the right 2 units. And then it's understood that the rest it has the same shape as the square root of x. Part B of this wants me to compare the graph of the square root of x to the square root of x minus 3. And that's just going to change where the graph starts. Instead of starting at the origin or starting at 2 like in part A, it's going to start at 3. So when I graph this, my new graph, if I count over to 3, which is right there, there's where the graph starts, and it's just shifted over. If I drug the graph over 3 units, it fit perfectly and be an exact copy of the initial graph. So I'm going to be lazy again and describe how these graphs relate to each other. The square root of x and the square root of x minus 3. They're exactly the same, except the square root of x minus 3 is shifted to the right 3 units. So in general, if I put a number inside a parentheses of a parabola function, x squared, under the absolute values if I put a minus, or under a square root if I put a minus after the x, is going to shift the graph to the right. The next problems are just to make sure you kind of understand the concepts. Problem 4, it says just describe how each one of these graphs would relate to a common graph. And for part A, it gives me a square. So this graph right here, it would have the same shape as, I'll say f of x equals x squared for that matter. Or I can say it's the same shape as x squared, except it's not going to have its vertex at the origin. It's going to have the vertex on the x-axis at 7. Except it's going to be shifted to the right 7 units. For part B, this graph is going to have the same shape as the square root of x, except it's not going to start at the origin. It's going to be shifted to the right 11 units. And part C, this graph is going to have the same shape as f of x equals the square root of x, except it's going to be shifted to the right 9. It actually isn't restricted, the shifting to the right, to parabolas, square roots, and absolute values. Not that this is on the handout, but if I gave you a function like this, f of x equals x cubed, and f of x minus 4 equals x minus 4 cubed, that graph, if I compare those two, the second graph is going to be shifted 4 to the right. So if I just to show you that I did 3 different styles of functions, parabolas, square roots, and absolute values, but this shifting to the right isn't limited to those. If I graphed these 2 functions on the same graph, specifically x cubed and x minus 4 cubed, the second graph is going to be the same as the first graph, except it's going to be shifted to the right 4 units. So there's the x cubed function, there's the x minus 4 function, x minus 4 cubed. So it's not restricted. I showed 3 styles of functions, but it's not restricted to that. Or even if I did something like this, if I compared 1 over x vs 1 over x minus 5. This is going to be hard to see, but if I graphed 1 over x, which is your nice, oh, I have the other graph on there still, which is, looks, we're going to need to clear this out of here, which is this, well, it looks like this. And if I compare that to 1 over x minus 5, I'm going to get exactly the same graph. It's a rigid transformation. If I could actually enter it right. And it's going to be moved over like this. So this is going to be over here. It's going to look like that when I graph it. And let me turn off this top one so we don't, it's going to be hard to see both graphs at the same time. And so the new graph is the same, except it's moved over 5. Maybe I can put that old graph on there and it might not mess it up so much. Kind of. Yeah, you can kind of see that the graphs are shifted. So this putting a minus in a parentheses or under an absolute value or inside a square root will work for any function. If I start off with a function that has just an x in it and I replace the x with an x minus a number, that new graph is going to be transformed by being shifted to the right. So this is not a limiting. The examples that I showed weren't the only examples. There are tons and tons more examples I can do. In this section, we're going to be doing 6 different kinds of movings of the graph. And the beginning one we did is moving something to the right. These next ones, it's counterintuitive, but they're going to be moved to the left. So problem 5 here says graph f of x equals x squared, which is a parabola, and then graph f of x equals x plus 3 squared, and describe how the graphs relate. I know that the f of x equals x squared is a parabola that has its vertex at the origin. So let me just graph that again, x squared, and so that's just that generic parabola vertex at the origin. And when on the same graph, if I graph parentheses x plus 3 squared and hit my graph button, it actually moves the graph instead of to the right, to the left. The new graph that my calculator just drew is a rigid transformation, meaning these graphs would fit perfectly on top of each other. The new graph has a vertex at -3, 0 as opposed to 0, 0. And how am I going to describe this? I'm going to be lazy, and instead of saying it's exactly the same, I'm just going to say it's shifted to the left 3 units. So it's kind of counterintuitive. The first group of problems when I had a minus in a parentheses or an x minus under an absolute value or an x minus under a square root, it moved the graph to the right. This next bank of problems where I have a plus, where I had a minus in the last problems, are going to move the graph to the left. Similarly, this part B, the f of x equals x squared that I'm comparing to has a vertex at 0, 0. This x plus 4 quantity squared, when I go to graph it on my calculator, if I count out to see the vertex is going to be at -4, 0. So when I go to graph this next function, instead of having a vertex at -3, it's going to be slightly over at -4. As a matter of fact, let me just show all 3 graphs together. So I'll do x plus 4 squared. And there's the x. So it's just moved over one more. So from the initial graph, the x plus 3 got shifted to the left 3 units. The x plus 4 from the x squared gets shifted one more, or gets 4 to the left. The nice thing about these is the number of units that it's shifted is you can just see it. So this graph is going to be the same as that of x squared, but it's shifted to the left, and the number of units is 4. Works the same with absolute values. The absolute value of x function is just this generic V shape. with its point at the origin. The absolute value of x plus 2 is going to be a generic V shape as well. Let me just graph both of these. I'll clear this junk that's in there. So to do the absolute value, you hit your math key and then number and then absolute value, or ABS. So the absolute value is still just generic V. If I wanted to do the absolute value of x minus 2 on the same graph, I hit my math key, go to number, absolute value. I'm doing x plus 2, should I say. And when I graph that, I get exactly the same V. It's a rigid transformation, but instead of having the point at 0, 0, it has the point at negative 2, 0. So these two graphs are exact copies of each other, but the new graph is shifted to the left 2 units. For part B, if I'm comparing the graph of f of x, the absolute value of x plus 4, to the absolute value of x, it's going to be the same, except the v, the point of the v is going to be at negative 4, 0, and it's going to be shifted to the left 4 units. So again, I'll graph all 3 of these so you can see all 3 graphs. So this third graph that I'm going to do, the x plus 4, when I graph it, it's even going to be 2 more over. So I have all 3 graphs. All 3 of those graphs would stack right on top of each other perfectly. I'm comparing part A and part B to the initial graph of the absolute value of x when I'm describing the change. So if I took out the middle graph here, you'd see that the new graph in part B is the same as the initial function, except it's 1, 2, 3, 4 over. Works again with square roots. This putting a plus sign after the x works with square roots, absolute values, squares. It would work with the fraction 1 over x. It would work with the function x cubed. And then hopefully you could sketch really crude graphs of both of these without even breaking out your calculator, because we know what's asked of me initially is to graph the square root of x. The square root of x is just a half a parabola on its side, and putting a plus sign under the radical, what it has the effect of doing, it has the effect of dragging the function over 2 to the left. So this is going to be the same shape as the square root of x, but it's going to be shifted to the left, and it's going to be shifted to the left 2 units. And I'll graph those both on my calculator so you can see them. So the first thing I wanted to graph was the square root of x, which is a nice half parabola on its side with the starting point at the origin. And when I go to graph the second square root of x minus 2, the minus being that below the times key, I get I was supposed to do plus 2. When I do the graph of x plus 2, as opposed to minus 2, sticks it right where I want it to stick it. It has a starting at negative 2, 0, as opposed to 0, 0. And for part B of this, the initial square root of x starts at 0, 0. This graph is going to start at negative 3, 0. It's going to have the exact same shape as the square root of x, but it's going to be shifted to the left. In this case, 3 units as opposed to 2. And I can graph that real quickly by changing the x to x plus 2 to x plus 3. All that does is move it over 1 more to this negative 3. And again, this would work if I graphed, I compared x cubed to x plus 5 cubed. This graph would be shifted to the left 5. If I compared 1 over x vs 1 over x plus 5, this would be shifted to the left 5. So it's not restricted to x squareds, square roots, and absolute values. It spans to anything. If you change any x to an x plus a number, put it in a parentheses, under an absolute value, or under a square root, it's going to move the graph to the left. Question 8 is just to make sure that we understand what's going on here. It just says describe how these graphs compare to a common graph. For part A, this graph is going to have exactly the same shape, and I'll be slightly more lazy here, as the graph of x squared, except it's going to be shifted to the left, and it's going to be left 7 units. Part B, the graph, if I graph that function, is going to have the same shape as the square root of x, but it's going to be shifted to the left 11 units. In part C, it's going to be a V because of the absolute value. This graph is going to have the same shape as the absolute value of x, except it's going to be shifted to the left 9 units. Towards the end of this handout, or the end of this section, I wrote up some boxes, and this box, which is the second box or table, talks about left and right shifts, and it very specifically kind of tries to hint out, if I put a number inside a parentheses and it has a plus, it's going to shift the graph to the left. If I put a number after the x inside a parentheses, which also includes under an absolute value or under a square root, and there's a minus, it shifts the graph to the right. So I usually say, inside parentheses, which is the same as under a square root, or inside an absolute value, and x minus shifts the graph to the right, and an x plus shifts the graph to the left. So that's 2 of the 6 shifts that we're really responsible for. The next shifts we're going to do are up and down shifts. And to move something up or down, you're not going to be making a change of under the absolute values or inside a parentheses. It's going to be after the function. So this lecture problem 9 that's coming up next, you'll notice that this function, I'm asked to graph x squared again and compare it to the graph of x squared minus 3. This is also a rigid transformation, meaning the second graph can be slid onto the first graph and it would fit perfectly. I want to describe how the graphs compare, and this is different because that minus 3 isn't in a parenthesis. So if it said x minus 3 quantity squared, I would say this would go to the right 3. But because that 3 is not in the parentheses, the graph's not going to move to the right. So the difference between problem 9 and problem 1, which both compared graphs to parabolas, is where the minus was. In problem 1, the minus was in the parentheses. In problem 9, the minus is not in the parentheses. So I'm going to graph x squared and x squared minus 3 and show you how that impacts it. And how this impacts it is it takes the graph and it drags it down 3 units. It almost makes it look like these 2 graphs wouldn't fit in each other, but it would. If I slid the top one down or the bottom one up, they would fit perfectly. So what this does, it takes the parabola that normally has a vertex at the origin and slides it down and makes it have a vertex at the point 0, -3. But it is exactly the same shape. Even though it looks a little bit wider, it's just because it's pulled down. It looks wider, but it's not. This has exactly the same shape as the graph of x squared, except it's moved or shifted down 3 units. So again, part B is different than question 1. If I gave this function x minus 4 quantity squared, this graph would move to the right 4 units, but x squared minus 4, the 4 not being in the parentheses, when I graph it, it's going to move the graph down 4 units. So when I graph x squared, get the parabola at the origin, and x squared minus 4, I get another parabola that would slide and fit perfectly onto the first parabola, but its vertex is at -0, -4. And again, I'm going to say this graph is the same shape as x squared, but it's moved down 4. I'm getting progressively lazier in what I write, and that's probably more common than not, to not get really wordy when you're writing how the graphs compare to each other. Just a few keywords are going to be important. So again, problem 10 wants me to compare the absolute value of x graph to some other graphs. The absolute value of x is that nice v that has its point at the origin. This graph, the absolute value of x minus 2, would be the same as the absolute value of x but right 2. This graph, the absolute value of x minus 2, you notice the minus isn't under the absolute value. This is going to produce something that gives me the exact same graph, except instead of being moved to the right, it's going to be moved down. So minuses in a parentheses or under an absolute values move it right. Minuses after the absolute value is going to move the function down. If I graph both of these, do math, number, absolute value of x, that gives me my nice v centered at the origin. And then if I add to this math, number, absolute value of x minus 2, I get another, I did it bad. What I did is I put this minus in a parentheses, and that was the wrong thing to do. I'm supposed to put it not in the parentheses. It's supposed to be after the absolute value symbol. So the x, I needed to cap out my parentheses there, otherwise it's going to think the minus 2 is under the absolute value. And now when I hit graph, it does what I want it to do. It goes down 2 units. So this would be a lazy answer, rather than saying it's the same shape as the absolute value of x, but it's shifted down 2 units. If I just said it's moved down 2, the other part's implied. Similarly for part B here, the initial absolute value graph has a vertex at the origin. This graph is going to have a vertex that's 4 units lower. And I can just say, I would be content with that. But if you weren't content with that, you can say this has the same shape as the absolute value of x, but except it's shifted 4 units down. And that would be fine to see. And I didn't even graph this, so let me just show you that that works. If I change the absolute value of x minus 2 to minus 4, hit my graph button, I get the absolute value whose v, the point of the v, is at 0, -4, as opposed to 0, -2 or 0, 0. Works with square roots just as well. Again, this is different. The square root of x minus 2 with the 2 under the square root would move the graph to the right. The square root of x minus 2 with the 2 not under the square root is going to move the graph down. This second graph, when I graph the square root of x and compare it to the square root of x minus 2, I'm going to get 2 graphs that are essentially identical to each other, except the second's going to be moved down. Notice the difference between where the minus 2 was. If the minus 2 is under the radical, it's going to move it to the right. If the minus 2 is not under the radical, it's going to move it down. So I'm going to compare the square root of x, which is at half a parabola on its side, to the square root of x, close out the parentheses. If I didn't close out the parentheses and then I typed the minus 2, it would think the minus 2 is under the radical. To make sure the minus 2 isn't thought of as being under the radical, I need the minus 2 to be after the x and the parentheses closed on the x. And when I graph this, you'll see exactly the same graph. It's just shifted down 2 units. And again, I'm going to be lazy. and say this is just moved down 2. Again, I don't have to be lazy. I can say this has exactly the same shape as the square root of x, but it's moved down 2 units. For this next one, my first graph, the square root of x looks like this. The square root of x minus 3 is going to look like that. And it's going to be the same shape, but moved down 3. Again, this is different than this. This one would be moved to the right 3 as opposed to down 3. So where the minus is makes a big difference. If the minus is under the radical, which would mean inside a parentheses on my calculator, it's a right move. But if the minus is after the radical or after the parentheses, it's a down move. 12 just wants you to integrate your skills to make sure that you can do these skills, independent of the other problems. And this doesn't ask me to graph, this just asks me to describe how these graphs compare to a common graph. For part A, this would have the same shape as the graph of x squared, but it's going to be moved or shifted down 7. If it said this, if it said x minus 7 quantity squared, I would say it went to the right 7. But because the 7's not in a parentheses, it's down. Similarly, for part B, this graph would have the same shape as f of x equals the square root of x, but it's going to be moved down 11. And again, if the minus 11 was under the radical, then it would go right 11. In part C, this is going to have the same shape as f of x equals the absolute value of x, but it's moved down 9. And again, if that minus 9 was under the absolute value, it would move it right. So minuses can move it right or it can move it down. It just depends how the minus is presented. But inside a parentheses, under an absolute value, under a square root or under an absolute value, that's when it moves it right. If it's after the function, not in a parentheses, not inside the square root, not inside the absolute value, a minus moves it down. All of these are rigid transformations, meaning the shape doesn't get tweaked. It just gets moved. The next few functions have pluses, and again, this is different. Had this function said x plus 3 quantity squared with the 3 being in a parentheses, that would move the graph left 3. This graph that I'm asked to do, I'm asked to compare the graph of x squared to the graph of x squared plus 3. And when I do that, instead of moving it to the left, it actually moves it up 3 units. So the graph of x squared, I know, is a nice parabola with its vertex at the origin. This graph that has the plus 3 is a parabola with its vertex at the point 0, 3. So it's moved up 3 units. So I can say this graph is the same as that of x squared, but it's moved up 3 units. For part B, if this said x plus 4 quantity squared and the plus 4 was in a parentheses, the graph would be moved left 4. But because the 4 isn't in a parentheses, it's going to move the graph up. So when I go to graph this on my calculator is going to produce a parabola whose vertex is on the y-axis. And this graph is going to be the same as the graph of x squared, but it's moved up 4 units. So if I change my y2 to x squared plus 4 and hit my graph, I get a parabola. The vertex is on the y-axis at the point 0, 4. So this next group of problems will all have my graphs shifted up as opposed to left. So pluses can move a graph left or it can move a graph up depending how the plus is presented. Inside a parentheses, a plus moves it left. After the function, the graph gets moved up by a plus. works with absolute values the same way. If I wanted to compare the absolute value of x to the absolute value of x plus 2, that would move the graph left 2. But this particular function that has the plus 2 after the function is going to give me that same v. It's going to give me exactly the same shape as the absolute value of x, but it's going to be moved up 2 units. And when I go to do these on my calculator, I know that the absolute value of x is that generic v. This is also going to be a generic v, but it's going to be a generic v that's moved up 2 units. It's going to look something like that. So I hit my y equals, clear, graph the absolute value of x, which is that nice v centered at the, or point at the origin. And I want to compare that to the absolute value graph of x plus 2. I have to close out the parentheses there around the x. If I didn't close out this parentheses, it would think the plus 2 was under the radical. And now when I hit graph, you can see that it's up 2. For part B, I'm comparing the absolute value of x to the absolute value of x plus 4. And because that 4 is not under the absolute value, it's going to move the graph up 4. When I hit my y equals button, change the 2 to a 4, hit my graph, you can see that the new absolute value is going to be up 4 as opposed to just up 2. So this, I'm going to be lazy. I'm going to say it's shifted or moved up 4 units. So I'm just describing how the graphs compare, and when they're exactly the same shape but just moved, just the move part is all I usually show. This will work with square roots as well. Square roots you can move up with a plus, you can move left with a plus. Had the problem that I'm about to do ask me to compare that graph, this graph would be moved left 2 from the square root of x, but the square root of x, when the plus 2 is not under the square root, is going to move it up. And then real specifically, the square root of x normally looks like that. This graph is going to move up 2 and look something like that. So if I graphed both of these like I was asked to, graph the square root of x and then the square root of x, close out my parentheses so that makes the plus 2 not under the radical. If I didn't close out that parentheses, it would think the 2 is under the radical, which it isn't. And when I do my graph, I see the generic half parabola on its side, and then a generic half parabola on its side, but moved up 2 units. So this is going to be the same shape. The graph of the square root of x plus 2 has the same shape as the square root of x, but it's shifted up 2 units. And this last one is going to be the same shape as the square root of x, but it's shifted or moved up 3 units. So, and I'm not going to have to graph these, but I should be able to predict what the graph is going to look like. So when I do this square root of x plus 3 graph, I get there's a generic half parabola on its side, and that's the thing moved up 3 units. So with pluses can move something to the left, or it can move something up. Minuses can move something to the right or down. These next 3 problems, again, just want to scramble this a little bit. Describe how this graph compares to the graph of x squared. G of x equals x squared plus 7 would be the same shape or the exact same graph as the graph of x squared, except this is going to be moved up 7 units. Again, had it said this, x plus 7 squared, I would say move it to the left. For part B, to compare the graph of the square root of x plus 11 to the square root of x, this is going to have the same shape as the square root of x, except it's going to go up 11 units. And again, had that 11 plus 11 been under the radical, that would move it to the left 11. And then part C, this graph would have the same shape as the absolute value of x, but it's going to be up 9. And again, had I put the plus 9 under the absolute value, it can move it left. So pluses can move something up or it can move something left. Minus can move something down or move something right. Okay, that's the end of that. And in my little boxes at the end, the top box is up and down. Basically, the first thing says if you add a number after the function, it raises it or moves it up. If you subtract a number after the function, it moves it down. This is what this box basically says. So after or not under the absolute value, not under a square root, and not in a parentheses, but after, plus moves up, minus moves it down. Whereas the second box says from inside a parentheses, under a square root, inside an absolute value, minus moves it right, plus moves it left. So plus can go left or it can go up, minus can go down or it can go right, depending on where that minus or plus is. The last things we're going to look at that are going to be test-worthy are throwing minuses into the situation. And a minus can flip the graph over the x-axis or I can flip the graph over the y-axis. And that's the next few problems that are coming up. So problem 17, lecture problem 17, says first graph f of x equals x squared, and then compare that to negative x squared. So I'll do that and describe how they compare. So I'll do graph of x squared, which I know is just a generic parabola with its vertex at the origin. And next I'm going to do negative x squared. The negative is going to be the negative in the bottom row of the calculator. And then x squared with no parentheses. And that graph is going to be this. And I see this is the same shape, but it's reflected over the x-axis. They're mirrored images, and the x-axis is the mirror. So this is going to be the same. These graphs are the same, but the new one is reflected or flipped over the x-axis. A lot of times I'm just going to say it's flipped over or turned over, which would be fine. Problem 18 wants me to compare the graph of x cubed to the graph of negative x cubed. It's going to be a lot harder to see this because x cubed is not such a nice function to look for transformations on. So the graph of x cubed looks something like this. The graph of negative x cubed is going to flip it over the x-axis. It's going to take this part that's down here, flip it over the x-axis, take this part up here, flip it over the x-axis. So when I do my new graph, this bottom part is going to be shifted above the x-axis. This top part is going to be shifted below the x-axis. Putting a negative in front of an x flips the graph over. So when I do negative in the bottom row of my calculator and x up arrow 3, that new graph, it almost looks like the two parabolas again, but it's not really because you can't. They're not color coded. You can't tell the graphs apart or the flips so well. But this is what happened. That the top part went down, the bottom part went up, and this graph was reflected over the x-axis. (19) wants me to compare the graph of the square root of x via the graph of negative square root of x. And you can start to see a theme here. I compared x squared via negative x squared, x cubed via negative x cubed. When I do this, when I do the graph of second square root of x, which is that half parabola on its side, so this square root of x looks just like this. And when I, on the same graph, put the negative second square root of x, and graph it, the second graph graphs like that. It's a carbon copy of the first graph, just reflected over the x-axis. So for each of the last three problems, the new graph is flipped over or reflected over the x-axis. To get a graph reflected over the x-axis, I just put a negative in front of the function. 20 is going to do the same thing. 20 wants me to compare the absolute value of x vs the negative absolute value of x. I know the absolute value of x looks like that. Putting a negative in front of a function flips it over the x-axis. This is going to be the new graph. So the new graph, if I do them both, do y equals clear, clear. If I did first math number absolute value of x, I get that nice v centered at vertex at the origin, or point at the origin. And then if I do a y2 math number absolute, whoops, forgot the negative, negative in the bottom row of the calculator, math number absolute value of x, hit my graph button, I get exactly a mirrored copy flipped over the x-axis. So throwing a negative in front of a function flips it over the x-axis. We'll notice problem 21 is a little bit different. I'm comparing square root of x vs negative square root of x. What I did earlier is compare x vs negative square root of x, and this right here flipped over the x-axis. Notice the negatives are in different places. In each of the last four problems, the negative was in front of the function and not under the radical. When I do this, when I do first, if I just clear these out, do first the square root of x, graph that, that's just a generic half parabola on its side. And if I compare that to and put the negative under the square root as opposed to in front of the square root, it's actually reflect the graph over the y-axis. So these graphs look, the original graph, the half parabola on its side, the new graph, half parabola on its side, and I'd say that this reflects the graph over the y-axis as opposed to the x-axis. So the difference with the negative, a negative in front of the square root, or multiplying a function by a -1 flips it over the x-axis. Replacing the x with a negative x flips it over the y-axis. It's harder to show flips over the y-axis. Let me show you these two, comparing the square root of x plus 2 vs the square root of negative x plus 2. And again, what that's doing is changing the x to a negative x. And that's different. I should probably do also vs negative square root of x plus 2, just so you can see what effect putting negatives has. So this is probably nice. So the square root of x plus 2, I know how to graph it. Second square root, x plus 2. It's going to be shifted to the left 2 units. So there's the square root of x plus 2. It's the same as a graph of the square root of x, but it's shifted left 2. Now if I hit my y equals and do this function, change the x to a negative x, watch what happens. It takes it and it flips it over the y-axis. So it takes this whole graph and it just turns it over, and so it makes it go in the opposite direction. We say that it flips it over the y-axis. So it takes the top part that's on the right part of the y-axis, flips it over to the other part. This part here that's on the left part of the y-axis, it flips it over. So it takes each part, so like this graph, if I wanted to look at this graph, this part of the graph here gets moved there, and this part of the graph here gets moved there. The whole graph gets reflected over the y-axis. So this graph, when I replace the x with a negative x, it reflects the graph over the y-axis. Harder to see with a more complex function, but the y-axis shifting is just harder to see just in general. Now if I do this bottom function, compare the square root of x plus 2, which is this nice function like that, to the negative square root of x plus 2, and hit my graph, you'll see that still just gets reflected over the x-axis. And it's a lot easier for me to see x-axis reflection. So this graph right here is just reflected over the x-axis. So putting a negative in front of a function, even if it's not just the generic square root of x or generic x squared, it's going to take the graph and reflect it over the x-axis. Changing the x to a negative x reflects the graph over the y-axis. Usually we say multiplying an entire function by -1 reflects it over the x-axis. Changing the x to negative x reflects it over the y-axis is kind of what we generally say. 23 is the same sort of problem. It's asking me to replace a negative x with an x. So I'm comparing the square root of x plus 3 vs the square root of negative x plus 3, and this graph is going to be reflected over the y-axis. And I can beat my calculator to the punch here. The graph of the square root of x plus 3 is shifted left. It's a parabola that looks like that. Changing the x to a negative x takes this part, moves it over here, and this top part and moves it over here, I guess. So I think this is what the new graph is going to look like. So this right here, this is the graph of the negative x plus 3. It's the graph of the square root of x plus 3, but flipped over the y-axis. So if I do y equals, clear, do first, second square root of x plus 3, clear out what's there. That's just so my half parabola on its side shifted 3 to the left. And then my new graph, second square root negative x plus 3. When I do that graph, I get exactly what I drew. It's just that graph reflected over the y-axis. So each half gets reflected to the opposite side of the y-axis. 24 is the same deal. It takes a graph and reflects it over the y-axis. This might be easier to see. So it wants me to compare the square root of x minus 5 vs the negative square root of x minus 5. The square root of x minus 5, this graph, is going to look like that, a half parabola on its side. So let me do both of these, just so you can see. So second square root, x minus 5, and then second square root negative x minus 5. So what these have in common is I replace the x with negative x. Here's the square root of x plus minus 5, half parabola on its side. There's the square root of negative x minus 5, which is over here at negative 5, and it looks like that. And that's a perfect reflection over the y-axis. So negatives, if you just change the x to a negative x, it reflects the graph over the y-axis. If you multiply the whole function by a negative number, so this function, the square root of negative x minus 5, this would be reflected over the x-axis. So if I want to look at pieces, this is the square root of x minus 5. This is changing the x to a negative x that reflects it over the y-axis. And if I put a negative in front of the function, as opposed to changing the x to a negative x, it reflects over the x-axis. So let me just show that all on the same graph. So if I did negative square root of x minus 5. So these are the three functions. And there comes the new one. It's reflected over the x-axis. So negatives can reflect over the x-axis. It can reflect over the y-axis. For a negative to reflect over the y-axis, any x in the problem gets changed to a negative x, and that will take the initial function and flip it over the y-axis. If I take the initial function and multiply the whole thing by a -1, it's going to reflect it over the x-axis. So negatives move across axes. Putting a negative in this little box says, putting a negative and multiplying the whole function by a negative flips it over the x-axis. And this box says if you change the x to a negative x, it reflects it over the y-axis. That's all the warm-up that we need, believe it or not, to be able to do the homework that's required for this section. So what we're going to need to be able to do is to use all these rules combined together to discuss how graphs move without actually graphing. So, problem 2 says describe how the graph of this function would compare to the graph of a common function. The common function I'd be comparing to is x squared because of the squared. So this graph right here is going to have the same shape as x squared, but it has two moves. And this part of it, the x minus 5 inside the parentheses, is going to move it to the right. Five units. And the +2 that's after is going to move it up 2 units. I don't need to graph it. This is what the problem is. That's the answer. But I can show you that I'm right. I predict that my graph should look something like this, meaning it should have a vertex of 5, 2. In order to be shifted 5 to the right and 2 up, doing 2 shifts in one, this is how the new graph would need to look. And let me make sure I haven't messed up here. So I should be able to predict what the graph is going to look like by just looking at the equation. Because it's a square, I know it's going to be a parabola. The minus in the parentheses moves it right. The +2 after the square moves it up. Let me make sure that my guess is a reasonable guess. If the graph that I get on my calculator is different than the one that I drew, then I messed up. So when I graph it, I get a parabola, and that if I count over, I get 1, 2, 3, 4, 5, and up 2, and which was by 1, 2, 3, 4, 5, and up 2. So it's perfect. My calculator and my prediction is right. The only thing I need to write for this is if I just had shifted right 5 and up 2, that would be enough. Problem 4, I need to describe this graph. This graph is going to have the same shape. As the square root of x, and I have to decide how it's moved. This part, the -1 under the square root, it's going to move it to the right, but it's moved or shifted right 1, and the -4 that's after is going to move it down 4. And this is all I'd have to write for number 4 for my answer, but I'm going to make sure I'm right because I'm going to draw a square root. I know a square root is a half parabola on its side. I'm going to go right 1, down 4, and I'm going to graph it on my calculator. My calculator graph should look something like that because this is a half parabola on its side, move right 1 and down 4. So let me check to make sure my answer is right. There's no algebra to do, so it's easy to make a mistake. So I entered this function basically exactly how I see it. I hit my graph button, and I look at my calculator's graph, I look at my graph, that looks pretty good. That's right 1 and down 4. So my answer is right. I've confirmed it's right because I drew the shape and it matched my calculator shape. 6, I want to compare this graph. This graph right here is going to have the same shape as the absolute value of x, meaning it's going to be a v. This part is going to move it right 5, and the +4 is going to move it up 4. So I'm going to say, except it's shifted or moved right 5 units and up 4 units. And again, I can tell you what the graph is going to look like. It's going to be shifted 1, 2, 3, 4, 5 to the right, 1, 2, 3, 4 up, the graph should look something like this. It should be sitting in the first quadrant with a point of the v at 5, 4. I check on my calculator to make sure I haven't messed up. So I'm going to go absolute value, math, number, absolute value of x minus 5 plus 4, hit my graph button, and that looks exactly more or less like what I drew, so that's perfect. So all of these have been friendly, just 2 rule problems. The next problem is going to have 3 rules. And the next one's going to be a parabola. The graph is going to have the same shape as x squared, meaning it's going to be a u. The minus here, it's multiplying the function by a minus. It's going to flip it over. Or I can say it's going to reflect over the x-axis. It's not going to go over the y-axis. So for this, it's going to be, I'll just say it's flipped over. For me, that's what's going to happen to it. It's going to be upside down. And this part in there, it's going to move it to the left 1. And there, it's going to move it down 4. So it's going to be flipped over, moved to the left 1, and down 4. So I'm going to go left 1, down 1, 2, 3, 4, and have a parabola that's flipped over. That's what the graph should look like because it meets the criteria. Putting a negative, multiplying by a negative, that would be different. If I put the negative inside the parentheses with the x, it'd be reflected over the y-axis. But in this case, it's going to flip it over or reflect it over the x-axis. So to graph this, to make sure my guess is right, I go negative, the bottom row of the calculator, then x plus 1, quantity squared, minus 4, hit my graph button, it's flipped over, it's moved left 1 and down 4. So my guess was perfect, my answer is correct. Ten, because it's a square root, is going to have the same shape as the square root of x, which is a half parabola on its side. This is going to flip it over or reflect it over the x-axis. So instead of going up this way, that's going to flip it over to go that way. So I'm going to say what's going to happen to this. I could either say it's reflected over the x-axis, or I can say it's flipped over. This part under the square root is going to move it left 2, and that part right there is going to move it down 1. So I can predict what this graph looks like. Instead of a parabola being a half parabola on its side opening like that, it's going to open like that because of the negative. It's going to go left 2, down 1, and it's going to look like that as opposed to like that because it's going to be flipped over. Well, again, let me graph this to make sure I haven't messed up. Hit my y equals, clear, negative, second, square root, x plus 2, close the parentheses, minus 1. Hit my graph button, and exactly what over 2, down 1, flipped over is exactly what I thought it was going to look like. Again, this is the only thing you need to write for an answer. You don't even need to see that's the same shape. I know that it's going to be the same shape as the square root of x. 12 is the first one that has a negative where the x is in front of the x. This right here is going to reflect over the y-axis. So a negative being with the x, it directly attached to the x, flips it over the y-axis. This plus 2 moves it up 2. So in general, a square root of x would look like that. This is going to be moved up 2, and it's going to be reflected over the y-axis. So it should look something like that. And let me make sure. So this would be all I'd write for my answer. It's reflected over the y-axis and it's moved up 2 would be completely adequate description of the changes to this graph compared to the square root of x. And so I did this perfectly when I hit my graph button. Hopefully my picture is perfect. If I look at my picture and that picture, that's good. It's moved up 2 and it's flipped over the y-axis, and that's what I needed it to have happen. 14, because the x was changed to a negative x, because the negative's attached to the x, it reflects over the y-axis. And this plus 4 moves it left 4. So in general, the graph's going to be moved left 4, and then it's reflected over the y-axis. So let me just steal this from my calculator, because I'm not that visual. And this is going to be one of those where you get a half here and a half. I think it's going to be like this. This part's going to be reflected here, and it's going to look like that. But I will steal this from my calculator. I'm confident that this is right. I'm just not confident that I can draw it so nicely. So, because my visual skills are probably not what they should be. When I hit graph, it's exactly what happens. It doesn't really even look like it's shifted to the left 4, but that is what happens. The graph was shifted to the left 4 like this, and then it was flipped over the y-axis, and which almost makes it look like it was shifted right. But technically, first it was shifted to the left, and then it was flipped over, and that's how I get this bit of the graph. So the minus attached to the x reflects it over the y-axis. The plus under the absolute value shifts it to the left. It's a deceptive switch because the reflecting over the y-axis makes the left switch look like a right switch. Ooh, 16's got all sorts of things going on. Double negative. This negative in front of the square root is going to flip it over, or it's going to reflect it over the x-axis. This negative under the square root is going to reflect over the y-axis, and that plus 2 that's not under the square root is going to move it up 2. So in general, I'd have a square root of x that would look like this. I need to be moved up 2, reflected over the y-axis, and then flipped over. The graph that my calculator gives me, I think, is going to be this, because it's moved up 2, that's flipped over the y-axis and flipped over the x-axis. That's probably what I'm going to get. The nice thing is we're not required to graph, so you don't really have to predict how the graph is going to look. You just have to understand how the components tell the graph to change. But I'll see if I'm actually right. And if you're more visual than me, then you might see this way better than I see this. And that's essentially what I drew, other than it goes down further than I made it show. But it's because I didn't plot any points. But it has the same shape. It's up 2 and it's flipped over. It's just that I didn't go, it's supposed to be more like that. But it's because I'm doing such a crude graph and not plotting any points, this sort of variation is real easy to get. You can get messed up like that real quickly. Okay, so that's that style of problem. The next style of problem is similar, but rather than giving me a graph, it describes the changes, and I need to create the equation. So as I read problem 18, it wants me to create an equation that has the same shape as x squared. The only thing it has to be different, it has to be moved to the left 2 units. And to move something to the left 2 units, I know I need a square because I want something that has the same shape as x squared. To the left is inside the parentheses with a plus sign. So this function is going to be the same as that, but moved to the left 2. I can call this just g of x if I want to be lazy, or I can call it f of x plus 2. Or I can give it no name, I guess. This is probably what I wrote for my key because I didn't want to get fancy in my naming. So this, and I'm just really looking at the right side anyways, that function is going to be the same as x squared, but it's going to move to the left 2 because if I put a plus inside the parentheses, it moves something to the left 2. And then the name is whatever you care to name it. If you don't name it, I'd live with that just as well. Problem 20, I also want something the same name as x squared, same shape as x squared, so I know I'm going to have a squared. First thing I see is I need shifted to the left 3 units. To the shift to the left 3 units, I need an x plus 3 inside of parentheses. And then the down 2 units, I need a minus after the parentheses. And I'm going to just call this, I'll call all of these g of x just to be lazy. Otherwise it gets too hard to name them. So I can see both things here. The plus 3 inside the parentheses is going to move it left 2. The minus 2 after the function moves it down 2. There's no algebra to do. This is just understanding how to make an equation that has the moves that we're looking for. 22 also wants me to make a graph that has the same shape as x squared, which is nice. The first thing I see, it needs to be reflected over the x-axis. That means I need a negative, and that negative is not going to be with the x per se. It's going to be, in this case, in front of the parentheses. There's going to be a parentheses in this problem for the left flip. The negative is this going to flip it over the x-axis. If I put the negative inside the parentheses with the x, it's going to reflect it over the y-axis. Next thing I'm going to do is shift it to the left 2. To get something to go to the left, you need a plus sign inside the parentheses. The last thing I want to do is up 4. To get an up 4, I need a plus 4 after the parentheses. So this function would be reflected over the x-axis or flipped over. It'd be moved to the left 2 and up 4. And if I want to give it a name, I'm going to be lazy and just call it g of x. So we're getting to the end of the section. Hopefully, this is not horrible, because there's no algebra to do, so it's not a good thing on the test. If you don't understand it, it just kind of falls apart. So I want now a function that has the same shape as the square root of x plus 5. The only thing I need to have done to it, it needs to be reflected over the y-axis. And to reflect something over a y-axis, I have to physically change the x to negative x. So problem 24, if I insist on reflecting over the y-axis, the negative has to attach to the x and be under the square root in this particular problem. If it said over the x-axis, the negative would be, so if it said over, reflected over the x-axis, and it wanted the same shape as that, the negative would be here. So the difference of where you put the negative, if you attach the negative to the x, it flips it over the y-axis. If you put it outside the square root, it flips it over the x-axis. But I'm only asked for reflecting it over the y-axis. 26 wants me to do something the same as x squared. I want to reflect over the x-axis, so I need a negative in front of a parentheses. And I want to go to the right 4 units. To go to the right 4 units, I do that. And then I could name it if I care to. If you don't name it on the test, I wouldn't take points off. So if I said g of x equals negative x plus 4 squared, that negative is going to flip it over or reflect it over the x-axis. That plus 4, oh, mistake here. To go to the right 4, I need a minus. It's inside the parentheses, opposite sign. That would have been a bad mistake. A plus can move it left or it can move it up. A minus can move it right or it can move it down. And in this case, the minus needed to move it right. Hopefully you caught that mistake before I caught it. 28, 30, and 32 I think will be the last 3 problems that I do. And the very bottom part of the problems aren't going to be on the test. And I'll write solutions for those in my solution manual that you can check. But I won't hold you responsible for those. I know this is getting crazy long and I'm almost out of time. So this graph is a rigid transformation of the absolute value of x. I need to write an equation for this. I'm going to call this one f of x. I want to try to come up with an equation for this. It's a v, so I need an absolute value. I have to decide how it was shifted. And very specifically, this was shifted like this. It was shifted left 2 and down 3. So I need to come up with an equation that graphs into an absolute value, which means I need graphs into a v, which means I need absolute value symbols. And I need it not to be flipped over, which is nice. I need to move it to the left 2. To move it to the left 2, I'm going to put an x plus 2 under the absolute values because pluses can move up or they can move left. They move up if they're not inside of parentheses or under the absolute values. They move left if they're inside the absolute values or inside the parentheses. And down 3 is going to be that minus 3. Minuses could move right or they can move down depending on where they're located. So this equation, again, there's no algebra to do for any of these problems. You either get them or you don't get them. And to get them, you completely have to understand all the different movements that are possible. 21 is flipped over, but it's not flipped over the y-axis. 21 is kind of a square root function, but it's moved right 2. It's moved up 1, and it's flipped over the x-axis, or reflected over the x-axis. It's a half parabola on its side, so I know I need a square root. So when I go to write the equation for problem 30, the shape tells me it has to be a square root because it's half parabola on its side. The negative in front of the absolute value is going to take it and flip it over the x-axis. If it was going this way, that would be reflected over the y-axis, and I'd have to put a negative, but attach it to the x, not put it in front of the square root symbol. To get it to the right 2, right is inside the absolute value with a minus, and to get it to go up 1, that's after the absolute value with a plus. So this equation, if I graphed it on my calculator, and I can graph it just to show you that it works. In fact, I could have graphed the last one to show you that it works. If I took y equals and did negative second square root x minus 2 plus 1, hit my graph button, and that is that graph just with a slightly different window, or slightly, but it's, if I crunched my window a little bit, you might see it better. If I change my y's to go to the 5s, you might see it better. Otherwise, you can't see the 2 1s so well. Anyways, it's a correct. And for that matter, in this last one, I wanted to revisit it. If I graphed this function, the square root of x plus, the absolute value of x plus 2, and then minus 3, should graph just into that, which it did perfectly. Well, which it did perfectly, but you couldn't see it. And, I don't know if you saw that last one, so let me make sure you actually saw that last one. Y equals negative second square root x minus 2 plus 1, and that graph, good. Can barely see it, but it's there. So last problem I'm going to hold you responsible for is 32. You need to come up with this equation, and it's hard to tell whether this is reflected over the y-axis, but it's only flipped over. I'm going to move this graph, goes left 2, up 1, and it's flipped over. So it's flipped over, which is reflecting it over the x-axis. Those three things simultaneously can produce this graph. There might be other ways to do it. You might be able to reflect it over the y-axis and get something that graphs the same. So if you write a different answer than mine, but it graphs the same, you're fine. But just so for me, I'm going to do, I know I need a square like this because of the shape. It's a parabola. This negative is going to flip the parabola over, make it go upside down. Now I want to go left 2. To go left 2, I'm going to put an x plus 2 inside the parentheses, and to go up 1, I get a plus 1 after the parentheses. I'm going to check on my calculator to make sure that this function that I've written matches that graph at least reasonably well. So I'm going to go negative parentheses x plus 2 quantity squared plus 1, hit my graph, and it looks so much like that I feel good about that my answer has to be correct. So this is all you're going to be responsible for in this section. The rest of the problems, I'm going to write solutions on my answer, my solutions manual for, but you're not going to be responsible. These graphs aren't going to be moved. They're going to be made skinnier or fatter, essentially. Like the graph of x squared might look like this, and and then the graph of 3x squared. So this is something similar. It's asking you to graph the two functions and describe how the graphs relate. All of the graphs in 34, 35, and 36, instead of being moved or flipped over, they're going to be made fatter or skinnier. And the numbers and where how big the number is and where the number's at is going to impact whether the graph gets fatter or skinnier. And I'll show those on my solutions manual. If you care to look at the solutions, they'll be there. And if you want me to teach you these, I'll teach you these just fine. And come visit me and I'll do that for you. Basically, for these problems, there just says graph the original function, graph the new one, and describe how the graph compares. And I'll just leave it at that because you're not going to be responsible for those. Okay, so that had to be a monster long lecture. Hopefully my video hasn't timed out.